This is the second module in a series on CCDs and image processing, and this particular module deals with CCDs in astronomical instruments. We'll talk about the system aspects, how the optics work. We'll talk in some detail about readout electronics and very briefly about cryomechanics in the doer. Then we'll spend our time talking about things that either diminish or increase the flux in pixels compared to what is projected on them from the sky. So dealing with vignetting, dust spots, diffraction spikes, traps in the CCDs, glowing CCDs, bleed trails, ghosts, cosmic rays, charge transfer inefficiency, dark current, and a little bit about airplanes and satellites. And then at the end, we'll go through a rogues gallery of deficient images that exhibit these different features and see if we can identify those pathologies together. In astronomical imaging systems, the light that comes from sources that are infinitely far away arrives as plane waves. Those plane waves get a little bit crinkled as they pass through the atmosphere, and the angular deviation of that planar wavefront is what we call astronomical seeing, induced by temperature structure in the atmosphere, and that actually is what dominates the size of the image that's made by the optical system. Optical systems map angle of arrival into position in the focal plane, and as we'll talk about here when we talk about diffraction, those two variables, the angle of arrival and the position in the focal plane, can be thought of as Fourier conjugate variables. The distribution of light in the focal plane is related to the Fourier transform of the flux across the pupil, and a good reference on astronomical optics is a book by Schroeder that goes through all the various aberrations and properties of astronomical optical systems. It's worth always figuring out what's the relationship between an angle on the sky and spatial scale x in the focal plane, and astronomers call that the plate scale. So the plate scale is the angle subtended by a pixel. And if you think about this optical diagram here, in terms of a thin lens approximation, the ray that passes right through the center doesn't get deflected. And so it's easy enough to draw a little triangle here for yourself where this vertical distance is the focal length of the imaging system. You can think about a pixel length p of displacement in the focal plane and ask yourself what angle does that subtend on the sky, and it gives you a number of arc seconds per pixel. So anytime you're given the physical size of a pixel in microns, the focal length in meters, you can trivially compute what angle a pixel subtends on the sky. And for the LSST telescope, our 10 micron pixels subtend 0.2 arc seconds, and that number is judiciously chosen because we want it to be the case that we have at least 2 pixels spanning the point spread function that's created by stars on the focal plane. And the best seeing images that we expect are around half an arc second, and 0.2 arc seconds per pixel accomplishes that. The actual optical design of LSST is considerably more complicated than that example. It's a 3-mirror telescope. So the light comes down, strikes the primary mirror, is reflected up to the secondary mirror, bounces down to a tertiary mirror that's actually fabricated on the same piece of glass as the primary, and that produces a fast converging beam that impinges on the focal plane and makes images. On its way from the tertiary to the focal plane, it passes through a 3-element optical corrector that essentially corrects for aberrations in the optical train, and in particular the chromatic aberration of the Dewar window. So the Dewar window is actually one of these active optical elements. It has curvature to it. And one of the features of the LSST optical system is that if you do a ray trace through the system as a function of distance off axis in the focal plane, the on-axis light makes a point spread function that looks like that, and if you move out to the edge of the field, it actually hasn't deteriorated by much. The actual point spread function that we'll achieve is the convolution of this intrinsic optical point spread function with the seeing from the atmosphere. And it's designed such that atmospheric seeing dominates the optical properties of the system.
By the way, when you say a fast beam, that just means one that has a very steep angle?
So the question is, what does fast mean? That's an optical term which is really what's the opening angle of the bundle of rays that are impacting the focal plane. If that opening angle is really small, it's a slow optical beam. If it's really wide angle, it's a fast optical beam. And it actually comes from the fact that the surface brightness on the focal plane depends only on the F number of the optical system. The F number is the ratio of the diameter of the beam some distance z on axis. It's a dimensionless number. And if that number is small, it's a fast optical system. LSST is f1.2. You have a hard time buying camera lenses that are f1.2. So it's a very impressive optical design. Part of the optical train is actually band limiting filters. So LSST runs in 6 filters, UGRIZY, that span from the ultraviolet cutoff due to ozone in the atmosphere out to wavelengths where we no longer have the energy to promote photoelectrons in the silicon. And so this is a map of the filter pass bands multiplied by a canonical atmospheric transmission function times the quantum efficiency of the detectors, just to give you a sense. The CCDs clearly are part of a bigger instrumental system, and so shown in yellow is a CCD sitting in a notional dewar where a number of things have to happen in order for this thing to perform properly. One is there has to be a very precise mechanical registration of where this thing is placed and what it means to be flat inside the dewar. So there's a precise mechanical engineering problem that has to position this thing to tolerances of a few microns, and that's inside a vacuum system. The reason it's embedded in a vacuum system is that we have to cool the detector to about minus 100 centigrade in order to make the dark current completely subdominant. So that is achieved by going to a temperature that's actually considerably above the temperature of liquid nitrogen. The CCDs are really not all that cold. There's a thermal regulation system where there's some cold thing that the CCD is connected to through a thermal impedance. There's some amount of heat that flows in this direction, and so there's a delta T that's engineered between this cold sink and the focal plane, and there are trim heaters applied to the system that actually actively regulate the temperature to a few tenths of a Kelvin. So there's a mechanical part, there's a thermal part, and because this thing is made really cold, it has to be put into a vacuum dewar, and then the clocking and electrical readout systems for clocking and readout have to penetrate the dewar wall somehow and go out to the outside world to computers to do image processing. For LSST, we chose to put all the analog readout electronics inside the dewar so that we didn't have to run 3,000 analog channels through the dewar wall, and the data are moved through a dewar wall digitally. Okay? The other point to make is that because the LSST optical design has something in the middle of the beam, the cone of rays that come down and impact the detector are hollowed out. There's a portion of the beam here where there's no light. And so the footprint of the beam on any optical element upstream going all the way to the primary is this sort of annular donut looking thing. And we're going to come back to why dust spots on optical elements that are upstream manifest as donuts in the focal plane. It's a consequence of that fact. So how do you actually assemble a full CCD image on the telescope? And the answer is it's a multi-amplifier per CCD and a multi-CCD readout system. All those analog signals go through some signal conditioning chain, go to an analog to digital converter, and that pixel data is then merged with metadata about where is the telescope pointing, what time is it, that comes from the telescope control system, and that combination of metadata and pixel data constitute a complete image file. I want to talk some about how we actually do the readout electronics for a CCD output stage. And so this is an illustration of the analog circuitry that resides on a CCD. The charge flows in from the left, and the charge per pixel accumulates on a capacitor here, and that capacitor is what performs the charge to voltage conversion. So the voltage is perturbed by an amount delta V gate that depends on the amount of charge that you dump onto the capacitor. And then there's an output FET. This is chosen to be a field effect transistor rather than a bipolar transistor because we don't want any current flowing into this device. We don't want the charge to bleed off. So that's why this is an FET. And all this FET does is present at this point a replica of the voltage at this point. So it's a unity gain source follower in this configuration and just basically buffers the output. The trick, though, is clearly if I read 1 pixel and its charge is accumulated here, I have to get rid of that charge somehow before I read the charge from the next pixel. And that's the job of this reset switch up here, which when this FET is turned on, the charge dumps to this reference voltage and I'm ready to read out the next pixel. And so the sequence in which we take data is this voltage gets set to this level when I turn this switch on. So there's a spike, it stabilizes at a reference level. I measure that reference level, I dump the charge on the capacitor, I take the difference between the reference and the signal level, and that's what I attribute to be the signal per pixel. So the typical sensitivity at this point is a few microvolts per electron. And so it's easy enough to calculate what the capacitance of that sense node capacitor is, and it's small. It's about 160 femtofarads, approximately, sort of order of magnitude. So you should think of this as being a little tiny capacitor. I dump the charge on it, and I'm ready to go. So the sequence of reading out a single pixel looks something like the following. Step 1 is turn on that reset FET in the top left corner. That accomplishes 2 things. It dumps the charge from the previous pixel, and it actually sets the quiescent operating point of the gate. It biases this gate to an appropriate level. So it actually does 2 things. Then I dump the charge onto this output capacitor, and that produces a negative going perturbation of the voltage here, because charge is negative, and I measure the voltage change that is induced by that charge transfer. How that's actually accomplished in the serial clocking on the CCD, so here's a 3-phase CCD. These are the phases of the serial clock. This little static voltage here is the output gate, and further to the right is that sensing node where we're going to dump the charge onto the capacitor. So imagine I have the clocks arranged so that S1 and S2 are at a low potential, S3 is at a high potential. From the standpoint of electrons, that's an attractive thing. And so this is kind of a potential energy diagram where positive voltage is increasing downwards. And so you create these charge pockets where the charge resides stably. And then to get the charge to transfer from here over to there, you actually just raise the potential at this point, and then the charge goes doom doom and lands over on this side, and simultaneously you start transferring in the charge from the subsequent pixel. And this output gate essentially ensures that the charge flows in this direction and can never flow backwards again.
And the voltage is high enough such that the neutral repulsion of the electron is not enough to keep them from going down those potential wells.
That's correct. I mean, eventually there is a limit to how much charge I can pile in each of these serial register pockets, and that's what I would call serial register full well.
Okay.
The other quick point to make is that this circuit is not exactly linear. That if you write down all the equations of how this works, you don't quite get absolute linearity out of this. So you should expect some component of nonlinearity in the system. So if you were to attach an oscilloscope to the output of the CCD as pixels are being clocked out, here's the kind of thing that you see. You get this big spike of feed through when the reset FET is turned on. It stabilizes to the reference level, the charge gets dumped, and it goes to the signal level. So that's what a nice clean output trace looks like. You can then write down the various DC and clocking voltages that we have to apply to these CCDs now that we've kind of built up some knowledge about how these things work. So there are a bunch of voltages that are time independent. One is the drain of the output FET, which is the connection in the top right corner of that circuit diagram. The drain of the reset FET sets the potential to which the charge goes and also determines that quiescent operating point. That output gate is a DC bias that just makes sure the charge flows only in one direction. We talked about the fact that the exterior of the CCD has a buffer ring around it called the scupper to prevent charge from the bulk silicon from migrating in. There's a backside bias that we apply, which creates the vertical electric field that drives the charge down to the pixels. And there's some notion of CCD ground that I have to establish. It's frequently the case that there's a temperature sensor on the CCD that has a couple of connectors, 3 or 4 phases of parallel clocking, 3 or 4 phases of serial clocking. Those are dynamic voltages that get applied. The reset gate is a dynamic voltage that gets applied, and out of each amplifier comes the output signal, which is the video signal that we then digitize. The clocking of the CCD is driven by a logical state machine. So you should think of a logical array of bits, and each bit controls the state of the clocks, whether they're in a high state or a low state. And so you just step through a succession of digital states, and then things called level shifters convert that digital state into appropriate bipolar analog voltages that are applied to the CCD. And for our electronics, all these voltages are not controlled with little potentiometers, but rather controlled by digital analog converters so that it can all be tweaked up and customized. And there's a field programmable gate array on our circuit board, which is the onboard logic device that steps through these various sequences. And so when we command a readout of the CCD, that's a high-level command that's passed down to this logic that resides on board, that then tick, 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 goes through all these states and reads out the detector. This is a underappreciated aspect of just how clever CCD electronics are. And let's go through a little bit of detail what people call KTC noise, or the origin of read noise in these detectors. So we calculated what the capacitance of that sensing capacitor is, and it's a thermodynamic degree of freedom. And so if I set 1/2 CV squared equals 1/2 KT, I can trivially, with no great detailed mathematics, convince myself that the RMS voltage across that output capacitor suffers a variable voltage of thermodynamic origin, which really originates in the fluctuation dissipation theorem, that's the square root of KT over C. And all measurements that we make in physics, we strive to achieve either a thermodynamic or a quantum mechanical limitation to the measurement that we make. If we get to that point, you can't do any better. So let's go through that. So here's the temperature of the sensor, here's Boltzmann's constant, here's the capacitance, you plug in the numbers, and the RMS voltage is 150 microvolts. Okay, thanks a lot. That's not an informative set of units converted into electrons, and I get an RMS noise at the output of 100 electrons. And the conundrum here is that the read noise spec for the sensors in LSST is 8 electrons RMS, and I'll tell you something, 100 electrons is a lot more than 8 electrons. So if it were the case that our read noise was 100 electrons, in order for the Poisson noise from the sky to dominate over that, we'd have to gather 10,000 electrons per pixel of sky noise to not be read noise dominated. And so clearly we're not in that regime. Astronomical imaging systems do much better than that. And so the question is, how do CCDs circumvent this apparent fundamental thermodynamic limit? Yes, Nick?
You have 10 to the minus 14 farads for your capacitance at the top and 10 to the minus 13 farads in the middle.
It's 10 to the minus 13.
Okay.
Top one's wrong. Sorry, inconsistency. I'll fix it. So the question is, how do we get around this? Because clearly we get around it somehow. And here's the way we get around it. That CCD output network is really in some ways a low-pass filter. The low-pass filter is the Johnson noise that's created in the effective resistance to ground at that node. And so what you get at the output is a low-pass filtered version of the power spectrum of the Johnson noise of the output resistor. It's always the case that the RMS voltage is the square root of KT over C. That fact is true independent of the resistance that you plug in here. The RMS voltage here is always going to be that number. But its temporal properties depend a great deal on what this RC time constant is. And so here are two illustrative traces that have the same RMS, but they're clearly completely different in their temporal power spectrum structure, right? One of them has a whole lot more high frequency noise than the other. And that's exactly what's going on with the CCD output stage. It is the case that the output always has square root of KT over C of RMS voltage noise, but it's at very low frequencies. And so this is a plot of the power spectrum of the noise at the output stage as a function of changing the resistance. So if the resistance is really low, the power spectrum is low and this breakpoint is way over here somewhere. If I start increasing the resistance, the Johnson noise level starts to go up in the power spectrum, but this roll-off point starts shifting to the left. And there's a conspiracy that the area under this curve, which is the RMS voltage that you measure, is always the same number. But we can use the fact that we have this really long natural time constant in the system to our advantage by just look at the plot on the bottom. Imagine this RMS noise is kind of rattling around, and then boom, I do the charge transfer really quickly. This hasn't had enough time to go through a big excursion. And that's what correlated double sampling does. You introduce a voltage change in the system on a time scale that's short compared to the RC time constant, over which these thermal fluctuations become uncorrelated. So the sequence is the following. We reset the pixel by turning on that reset FET. When I do that, that's a low resistance connection, and so that essentially has high frequency fluctuations, but then as soon as I turn that off, it's kind of frozen. As soon as I turn off that output FET, it sort of freezes the voltage level. I measure the reference level. I quickly shift the charge onto the output node. I measure the new signal level before things have had a chance to change very much, and I measure delta V. So it's really basically doing time domain differential sampling over timescales that are short compared to the natural timescale. So how do you actually do that in an analog signal chain? Well, you capacitively connect the output to a preamp, and then that runs through two different gain paths, one with a gain of +1, the other with a gain of -1. Those are sequentially connected to an integrator, and we basically use the integrator and appropriate selections of gain to do this time domain differential imaging. And the only other thing that you sort of add in here is a little bit of a bias, because we want to use the entire dynamic range of the A to D converter to measure unipolar signals, and so we bias the signal up above ground in order to accomplish that task. There's one other sort of nuanced detail in here, and that is you don't want any memory from one pixel to the other, so there's an opportunity to just reset the voltage to 0 in the signal chain, if you so choose. So here's just an illustration of how that works. The top level is the video signal, where we start with a reference level, you throw the charge on there, you generate the signal level, and then you're on to the next pixel. This gain select essentially says, am I going to connect this video with a gain of +1 or a gain of -1 to the analog signal chain? That determines what's fed to the integrator. So it's only gated on for this interval of time, and here the video is fed through with a gain of +1. In this interval, it's fed through with a gain of -1. And here's what the integrator does. Nothing, nothing, nothing. And then the integrator starts to integrate this negative thing. It starts to integrate this positive thing. And this difference from 0 is a measure of how far apart those are from each other. And that's what we do. So the integrator also serves as a low-pass filter, right? Because if you take the integral of sine omega t, you get a 1 over omega, so it suppresses high-frequency noise. So that's what it does. And that's all implemented in the LSST electronics in a custom application-specific integrated circuit, which was made by our colleagues in France, that implements all this at the single chip level. It turns out that the preamp uses ratios of capacitors instead of ratios of resistors. There are lots of adjustable gains that you can put in there. It's quite a flexible thing, and it implements this dual slope correlated double sampling signal chain on a single chip.
Yeah, one of those for each.
We have one of those for each analog output amplifier. So there are 16 of those per CCD.
Well, there are 16 signal chains. There are 8 per integrated circuit. So there are 2 integrated circuits per CCD.
Right, but
eight of
each
those,
amplifier
yes.
each amplifier
Saves
has
that
one of
same
those.
signal chain. Yep.
Each custom IC has more than one of those inside
Yes.
it.
Okay.
8 of those in each of them. Sorry. Yep. Okay. So here's the layout of the LSST focal plane. The parts shown in blue are the science imaging array, where we aggregate up 9 CCDs into a standalone unit called a science raft. On the left is shown a corner raft, of which there are 4, And the corner rafts contain, shown in yellow, the guide sensors, which read out at 9 hertz and deliver tracking information to the telescope control system, and a pair of offset wavefront sensors shown in green that measure the shape of the optical system and the positions and shapes of mirrors in a way that we can talk about down the road. So it's a modular thing, and it's all implemented as shown. So here's just a blow up of what one of these science rafts looks like. There's a set of 3 electronics boards. Each electronics board reads out 3 CCDs, and it produces digital data that flow through the door wall off to the data acquisition system. The corner raft electronics boards are implemented slightly differently in terms of layout and implementation, but conceptually are identical to the electronics that resides on the science raft boards. It turns out that we actually run the LSST electronics at 18 bits per pixel. If you want a high resolution representation of the information, the number of distinct states you get is 2 to the n, where n is the number of bits. If I ran an 8-bit system, I actually get 256, not 156 states. That's a typo. And if you just ask yourself, we'd like to not be bit flip quantization limited, so I need to digitize the read noise with a fair number of bits, and what's the maximum full well I can possibly put through the system, the ratio of those two numbers actually exceeds 16 bits. And so since we can get AD converters that run at 18 bits, that's exactly what we're going to do. So we actually digitize at 18 bits, and as that information flows through the system, it gets converted into a floating point representation pretty early in the downstream image processing. So let's change gears from sort of system level engineering to think about factors that can diminish the flux in a pixel relative to ideal. So the first thing is vignetting. The optical system doesn't transfer 100% of the rays that are impinging on the front of the telescope. First of all, there's the entire instrument and secondary mirror in the way, right? It blocks a significant fraction of the light that's coming down the path. But it's also true that at the edges of the field, not all the parallel rays from a distant source make it to the center. Some of the rays get scraped off by obscurations in the optical system. Furthermore, just some general principles, if you sit back at infinity and look at the pupil of the system and rotate off axis, the apparent area of the pupil actually diminishes like A cosine theta. So even if everything else were absolutely perfect, we'd be losing a certain amount of light just because the projected area is going down. So there are lots of reasons why we don't get all the light through the system. There are other things that can obscure rays making it through. The shutter can fail, the filter changer can put things in the wrong position, maybe the mirror covers don't open all the way, maybe the dome hasn't rotated to the right place so you're vignetted by the shutter. All those things happen. At a more microscopic level, the sensor surface is contaminated by dust spots or depositions of chemical contaminants. So the pixels are 10 microns across. If I had a 5 micron dust spot land on one pixel, it attenuates the apparent sensitivity of that pixel. If I had a 100 micron hair land on the CCD, that then looks like a linear feature that's resolved, and you actually see it on the surface of the detector. So there are things that sit on the detector. There are also dust spots further upstream in the optical train. And whether they're on reflective or transmissive surfaces, now think about that illustration that I showed you really early on with that annular illumination of the upstream Dewar window, and ask yourself, if I put a dust spot on the Dewar window, what regions in the focal plane have diminished flux because of that dust spot? And the answer is any region whose annulus includes that dust spot has its flux diminished. And if you think that through, that region on the focal plane is also an annular distribution. And so dust spots further upstream look like representations of the pupil, and their size depends on how far upstream that dust spot resides. So we're not going to worry about other things that diminish flux, like atmospheric attenuation, clouds, contrails, birds, bugs, bats, drones, and trying to point through trees. We're going to limit our attention to things that are happening within the instrument and the optical train. But those all happen too. So this is a plot of what fraction of the incident rays strike the focal plane as a function of how far you are off axis for the LSST optical system. So the fact that it's sitting at 0.6 and not at 1 is the obscuration from the secondary and the instrument in the middle of the beam, and it's pretty flat until you start getting over to the edge, and then it drops like a rock, but our instrument only goes out to 1.75 degrees. So the vignetting in this system is really not very egregious, but it is enough that we have to take it into account, and that's compensated for in flat fielding, where you essentially compensate for the fact that sources at the edge of the field produce fewer photoelectrons than do sources at the center of the field.
So the flat fielding images will have some light come in from 1.75 degrees off to the side.
Yeah. So my answer to your question is, if the optical system does a good job of mapping exclusively angle of arrival into flux in the focal plane, and if there's no stray and scattered light, then the light that is at the edge of the field from a flat is impinging on the system at that angle.
Yeah.
Now, those assumptions are both not true, and there is contamination by stray and scattered light for sure. So shifting to dust spots, here's a picture from the CTI 0.9 meter where bright things are white and dark things are gray. This is an image of the sky, and in the blow up, all those little wiggles and bumps and squiggles and black things are filthy contamination on the surface of that sensor, and you can tell that because it's all in focus, right? It's actually sitting on the surface of the array, and you can see a couple of stars in that image as well. Here's a typical flat field that shows a heterogeneous distribution of annular things coming from dust spots that sit at different distances upstream. So the smallest annuli, I'm going to guess, are things that are on the Dewar window. That's the closest interface that can put occlusions in the beam. You can see there's a kind of intermediate size and then there's a big size, and those are each just marching further upstream. And if I knew the F number of the beam, I could tell you exactly how far upstream those occluding dust spots are, right? I can tell what's going on. So it's a pretty straightforward thing to figure out. Oops, sorry, went the wrong way. Another thing that can be a bad thing, shown on the left, is a really delightful picture of a contaminated Dewar window and detector, right? So if there's contamination in the optical train, that's really nasty and bad. And on the right-hand side, although it doesn't come through particularly well on the screen, there's a funny halo of crud here that's actually light from this bright source propagating through contamination and crud. So it has a pretty distinctive footprint. Another thing that can attenuate flux in pixels is actual traps within the detector. So this is an example of charge that gets, think about it this way. Let's start reading out the CCD. What happens is I read out this row first, then this row, then this row, then this row, then this row. But if there's a defect in the CCD that prevents charge up above from making it through that point, all the pixels that reside in upstream in the column don't make it. So there's an occlusion here in the CCD where I can measure charge down here just fine, but charge from this region of the array gets impacted, and you can see it ate the side of that star right there. All right, so bad pixels and bad columns are something that if there's a single bad pixel or column, because we've Nyquist sampled the point spread function, we can kind of interpolate over that. But if there's a big fat region of 10 adjacent block columns, that's a bad thing. So changing from things that can diminish flux to things that can actually enhance flux artificially, here's a blow up of a bunch of pathology from a CCD image. And this shows three different things. The vertical fat things shown with yellow arrows are bleed trails. So that's where the charge is actually blown out the top of the pixel and is bled along the column. But there's another fainter thing here also in the vertical direction. This thing And these things coming out to the side and this part coming down to the bottom are actually diffraction spikes off the top end of the telescope. And you can also see there's this funny circular offset pattern here. That's reflected ghosting in the optical system. So we'll talk about each of those in succession here as we go. So this is an example of where bright stars in the image have clearly bled out and have created vertical trails. If the star is really, really bright, it'll extend the entire length of the CCD. And some of the LSST detectors have what's called a midline implant, which is an imposed barrier halfway across the CCD to prevent these bleed trails on one half from bleeding all the way to the other side. It was an attempt to contain these. One of our candidate sensor vendors has that in the other one it doesn't. So we'll talk about that more as we go on here today. So that's what bleed trails look like. If you're a photon coming down into the pupil of the telescope, the support structure that holds the component of the instrument that is in the center of the beam actually produces diffraction. And so this is an example of where if you went through the Fourier optics calculation, if you want to think about it this way, it's like those things are little tiny single slits in emission, if you want to think about it that way, through Babinet's principle. And so the diffraction pattern that you see on the focal plane depends on the spatial structure of the support in the telescope. And most optical telescopes have a support structure like the second thing from the right. It's a symmetrical configuration of typically 4 of these things, and that's why the diffraction spikes in images look like that. This would be for monochromatic light. We're in broadband enough light that actually those interference, constructive and destructive interference regions are not nearly as sharply defined because we're in broad passbands.
And these support structures typically match the axis of the CCD. We see these spikes sort of going along pixels and rows of columns.
That's a great question. Hold the question about the orientation diffraction spikes and we'll come to it in a moment. So here's a picture from HST of really rather glorious diffraction spikes looking like Christmas ornaments. So this is the answer to your question. The LSST telescope has the support structure shown here for equatorial mount telescopes where the orientation of the instrument is locked relative to north and where the support structure of the secondary has no rotational degree of freedom relative to the instrument, then the diffraction spikes are always locked in place. So that's the case for the dark energy camera on the CTIO 4 meter currently. The LSST optical system, though, is an alt-az telescope that actually has 3 degrees of freedom. It turns out for alt-az telescopes, as you track across the sky, in the physical mount coordinates, the field actually rotates. And so we compensate that by having a rotator. The entire instrument is on a rotator whose rotation axis is parallel to the optical axis of the telescope. That means we can induce discrete rotational offsets and actually rotate the diffraction spikes relative to the sky in the different dithers of images that we take and do a better job of suppressing them. What's commonly done is to just mask the pixels that are associated with diffraction spikes as opposed to try to fit and subtract them out. But if I take enough rotationally disregistered images and median filter them, I've washed them out of the image. Here's a really remarkable example of ghosting in a CCD image where you can see a ghost that's coming from a reflection in the system that, you know, as the light is coming down towards the detector and is this converging cone, if I get 2 reflections off of 2 surfaces upstream, the effective focal length for that ghost is longer than the focal length for the actual focusing imaging path. And so you get an out of focus representation of the source, which actually matches the distribution of flux that's propagating through the system. And so there's this funny, distorted off-axis reflection coming from a bright source way over here. And if I were doing photometry of this little star right here, it's really not that much of a problem because all it's done is to locally boost the sky value by some amount that's uniform surface brightness. The problem are the discontinuous changes in flux, Like, how do I assign a sky value to this object that I then subtract out when it straddles this part of the ghost? So understanding where the ghosts are in the image and dealing with them appropriately is one of the challenges in the downstream image processing chain. Photons from the sky are not the only thing, optical wavelength photons from the sky are not the only thing that can create charge in pixels. We're also being constantly bombarded by cosmic ray muons primarily, and those cosmic rays happily deposit charge in the silicon when they interact. And so one of the image reduction challenges then is to discriminate these cosmic ray events from legitimate sources. One of the big standard methods that people use there is to take multiple images, because if these cosmic rays are random events that are completely uncorrelated, and if I median together the images, then I completely wipe them out. Here's a really interesting image from Hubble Space Telescope, where this has a bunch of stuff going on here that we can try and figure out and identify. So of all the stuff that's in this image that jumps out at your eye, it's very much the minority of all that that constitute legitimate astronomical sources. So if we sit here and try to identify the various features that are going on in this image, we can start to notice some stuff, right? So one thing that you see is this big, bright, ripping trail going across the middle of the image. And so is that if Hubble Space Telescope is pointed so that galaxies like this one are stationary in the image, that's something that's moving at non-sidereal rates. Another thing you can see is a picture frame around the edge where there isn't really any source coming from the sky, and there are all these little lines and things. There's a diffuse halo of stuff down the bottom left-hand side, and so the question is, what is all this? So the picture frame around the edge is a vignetted region of the sensor, and the only things in there are cosmic rays. The thing that streaks across the middle is actually another satellite in orbit imaged by HST as a streak. There are abundance of cosmic rays. Some of them are lines, some of them are points. They're all over the place. There's an actual, one legitimate source up there is a galaxy, and we don't yet know what this funny halo is on the bottom left-hand side, right? Could be some defect, could be condensation, who knows what. But an easy way to figure out is to just take another picture. And if you just take one more image with HST and invoke the world's most naive image processing algorithm, which is, please give me, of the two images, the minimum flux in the two frames, it actually cleans up to that. Because all those things that give you augmented flux that's uncorrelated completely go away. And so now you can start to see clearly things that are actual sources. And all that diffuse stuff in the bottom left is starting to look real. And if you then take 20 frames and stack them up, you start to get something that's looking a bit more like a real image on the sky. Okay? Another possible source of illumination in CCDs is actual, basically CCDs acting like LEDs. If there's electrical breakdown in the detector so that it basically glows, that produces light that lands on the array. That is sort of, in old CCDs, glowing amplifiers was a perennial problem. And this is an example of a glowing amplifier on the old Mosaic imager on the CTIO 4-meter telescope that we actually used for the Essence supernova survey. This is a 10-minute long dark frame, and you can see there's actually a lot of light coming from that glowing amplifier. And that can happen in amplifiers. It can also happen at the clocking gates down the side of the array. And so taking a long dark to see if anything's glowing is a really good idea. We talked about charge transfer efficiency. Here's an example where on the left, this is an image where an iron-55 radioactive source is sending X-rays onto the image. The left-hand side, you get nice tight point spread functions. On the right-hand side, with degraded parallel charge transfer efficiency, some of the charge is left behind in the vertical direction, and you get this asymmetrical streaking, which you can distinguish from bleeding because it happens for all sources, and it's only in one direction, and it's the direction where the charge would be left behind. Another thing that can happen is that the analog electronics just acts like an antenna, and there's pickup of radio frequency interference either through capacitive coupling to electric fields or inductive coupling to magnetic fields. And so if you see periodic modulation in a bias image, that's highly likely to be coming from some kind of RF interference in the system. And a particularly notorious source of that are switching power supplies. A lot of switching power supplies have a switching rate that sort of strobes nicely with the pixel rate in CCD cameras and is a notorious source of interference. And the problem here is that a simple bias subtraction won't fix this because the relative phasing of that thing rippling through is completely asynchronized with the pixel readout. You can go into the overscan and do some really complicated, clever thing where you say, well, let me fit to an amplitude and a period in the Y direction, a period in the X direction, and a phase, and try to subtract it out, but it's a royal pain in the ass, and it's much better to actually build a system that's immune to this. So here's an example of a CCD image where in a bias image, the signal per pixel exhibits a strong horizontal dependence. Right? It's a lot brighter on the left-hand edge than it is over in the middle and on the right-hand side. And that can come about for a couple of reasons. If there's some kind of bias instability in the readout electronics so that that offset that we introduce in the signal chain is variable over a row, it'll do exactly this. Another way I've seen this happen is if the serial clocks are derived from voltage references that are not stable enough when you start clocking serially, if the serial clock rails start to droop, some of the signal in each pixel is actually feed through from the serial clocks, and that clock droop actually manifests itself as an apparent bias shift. And so these guys went and actually measured as a function of temperature, and it's a non-trivial component that they'd have to deal with and eliminate. In this image that we looked at that had amplifier glow, in this amplifier up on the top, there's actually a bias instability that you can see running down the side of it. And so if you take that and blow it up, in one of their signal chains, there's a clear pixel-dependent, uniform for every row instability in the system. Another thing that can add fictitious charge is what's called image persistence. So these example images, shamelessly stolen from the web, on the left-hand side is a picture taken with a CCD camera where they really blasted it. You can see it's really kind of saturated in the center. And then they really quick took a 30-second dark frame with the shutter closed and read it out. And on the right-hand side, you can see a temporal ghost of the entire image that's on the left-hand side, because what's happened is some of the charge that was generated at the saturation level was driven into long-lived metastable traps in the detector that eventually relinquished their charge over a long time scale. And that's why they had to take a 30-second image to have that stuff all bubble out. And so there's a natural time constant associated with those traps as you get Boltzmann excitation of the charge eventually leaving those metastable states. So image persistence in successive images is another potential source, and this is the obvious way to test for it. Another example that doesn't show up so clearly on the projector screen, but's better on the laptop, is that there can be capacitive coupling between adjacent amplifiers, so that when this signal on the right-hand side reads a really bright signal level, you really can just barely see there's a ghost vertical band on the on this left-hand side that's much clearer on my laptop screen here than it is on the screen that you see. Okay? And that's a consequence of pixels that are read out synchronously can crosstalk to each other. And so anytime you see a bright source on one side and a ghost image on the other side at pixels that were read out at the same time, that's the signature of analog crosstalk. And that can be mapped out. We can actually measure what the contamination is from one amp to another and actually subtract out that component of the signal in a deterministic way, as long as the ADD converter captures the full saturation level of the image. so that we know how big the drive term is. So here's an example on the top right of the kind of crud that you see if there's a obscuration upstream in the optical system. Clearly, a lot of the light just isn't getting through to the focal plane, and that's because they had a filter wheel that was stuck. These are now some exercises to go over what we've learned. You can see on this image there's some crud in the bottom right-hand corner, and also a sort of diffuse scattering halo here in the center of the frame. And the question is, what could be causing that? And the answer is, this is pretty in focus in the image, and actually turns out to be a consequence of ice crystals condensing on the surface of the detector. Also apparently some condensation on the window of the Dewar. Those two things have different origins typically. One thing to be aware of is that if you cycle the Dewar that has the CCD in it in a way where there's ever an instance where the detector is the coldest thing in the Dewar, all the gases and water that are evolving off the Dewar wall or anywhere else that they were cryopumped will actually migrate to the surface of the detector and condense there. That's one potential origin of the ice crystals that grew on the sensor in this case. Another thing that has been known to happen with some frequency is the Dewar window actually can become colder than the dew point in the observatory where it's being used, and that leads to water actually condensing on the exterior window of the Dewar. So those are both things to be avoided. Here's another example image that has multiple pathologies, and so I'll pause for a moment while people consider what's going on in this frame. So apart from the obvious bad column that runs down the left-hand third of the image here, there are two things going on. One is this sort of modeled pattern of Newton's rings interference type effect. In addition, each of these stars has a trail going in one direction only. And so that's unlikely to be pixel full well overflow, especially because it appears to afflict every single star, not just the bright ones. And so those two actually come about from two different phenomenologies. The interference fringes that you see are actually because of Fabry-Perot resonances within the detector excited by bright, sharp emission lines from the night sky. And so that's what people call fringing within a CCD. That can be corrected for by actually subtracting from the image a scaled version of a fringe frame that can be obtained from either multiple dithered images median together or else from dome flats taken in narrowband light. This trail, I think, comes about because the shutter opened before the telescope pointing was actually stabilized, and then the telescope slides over to its stable position where then stable PSF is generated. Here's another example. This is actually the example that we saw before for crosstalk. So there's a bright star. You can see the ghosts from the pupil of the telescope. And over here on the left-hand side, the crosstalk. There's another anomaly in this image, though, and that is in this quadrant. After the bright column has gone by, there's some kind of suppression of signal, but not for every single row. And I actually don't know what causes that in this particular sensor. That's why there's a question mark next to it. So this is a fun image. This is now reverse grayscale representation where white things are faint light values and dark things are bright. And so I'll pause for a moment while you think about what might be going on in this picture. We can see a number of the things that we've talked about. There's a bad column running down the left-hand edge. Here are some things that are sitting on the surface of the sensor. But this funny little multi-leg spider-looking thing is actually because for this particular image, while the shutter was open, an earthquake came by and rattled the telescope. So that's actually the jitter of the bore side of the telescope, and this could be some resonance in the secondary or the telescope losing tracking across the entire image. So this is CCD imager serving as seismograph. So to wrap up this module, we've gone over the potential sources of systematic error that can afflict CCD images after they're integrated into an astronomical instrument. Many, and in fact most of these, can be suppressed in image processing software downstream. CCD readout systems that use correlated double sampling circumvent the naive thermodynamic limit, and then we're left with just the counting statistics imposed by quantum mechanics, so that these systems operate limited ideally only by Poisson noise from the sky. And finally, diagnosing strange features in CCD images is sometimes difficult and requires frequently physical access to the system and thinking your way through the light path, doing a few diagnostic tests, and unraveling what's going on. References for further investigation on this topic include a nice book on astronomical optics by Schroeder. There's a nice introductory book to Fourier optics by Goodwin. The Big Thick CCD Bible by Jim Janicek has a good description of different CCD electronics readout schemes. There's a nice classic article called CCDs, the Good, the Bad, and the Ugly by George Jacobi and colleagues. And there are some nice galleries online of problematic CCD images from which I have taken frames with attribution throughout this presentation.